Introducing Dr. Albert for this today's speaker. Personally, I've known him for quite a while. He was actually my PhD advisor. And I don't think he actually knows this, but he did influence me to get a PhD degree in mathematics. So kudos to you. Thank you for doing that. On an academic note, though, he's had about, I think, over 30 years of work in analysis, specifically in PDEs. And he's actually made significant contributions to the understanding of bound states, wave solutions, in particular when we talk about the existence, the uniqueness, and stability of these solutions to nonlinear equations and everything. So his talk today is actually going to be on the non-degeneracy of bound states, and I think it's to the NLS equation and its role in investigating the dynamics of other solutions to this equation. So join me in welcoming John Albert.
Okay, thank you. So this talk is not about my work. It's an expository talk. I just wanted to mainly go over a couple of classical results, which the nondegeneracy of bound states, which is a linear property of bound states, is used to prove results about the nonlinear dynamics of the nonlinear equations, the bound state solutions of. These results are, like I say, they're kind of classical, at least in the sense that they're 8 years old or more. One of them is maybe 20 years old. And they're results on the uniqueness and stability of bound states. So I will be talking about the NLS equation, as Ari said, which I've put up on the slide here. And also, a little bit later, I'll be talking about a fractional version of the NLS equation. The Laplacian is replaced by a fractional Laplacian. But a lot of the, or at least a couple of the theorems that I mentioned have natural analogs, or the methods used to prove them have natural analogs for many other nonlinear equations as well. The nonlinear Schrodinger equation does have some physical applications. For instance, it models waves on the surface of deep water. It also models, it does come up as a model in nonlinear optics and in Bose-Einstein condensates. I think Bose-Einstein condensates in a cigar-shaped trap. And there are also other equations which are closely related to the nonlinear Schrodinger equation, which come up in many other applications. For example, if you were to add dissipation to the nonlinear Schrodinger equation, you would get the Ginzburg-Landau equation, which comes up in theory of phase transitions and superconductivity. And then, well, for the application to water waves that I mentioned from the nonlinear Schrodinger equation is actually, this equation only appears in the one-dimensional setting. In the two-dimensional setting, if you want to model water waves, you would go to Davy-Stewart. But the nonlinear Schrodinger equation appears as one of the equations in the Davy-Stewartson system. So we'd want to understand the nonlinear Schrodinger equation to understand the Davy-Stewartson. And in general, if this is not exactly the model that appears for a given physical situation, it's a simple and natural model that you would want to understand very well before attacking the more detailed models which are closely related to it. But if you want to think about physical application, you can think about waves on the surface of one-dimensional waves on the surface of water. And this green picture that I've drawn here is actually something that you might see if you looked at one-dimensional sinusoidal wave surface of water. Not necessarily squeezed this tightly together, maybe stretched out more. But what happened on the surface of deep water is if you try and set up a sinusoidal wave, not very small amplitude, if it has finite amplitude, then modulations will creep in. You can't keep a steady sinusoidal wave with constant amplitude and frequency on the surface of water because of the Benjamin fire instability. And the modulations that creep in will look like this. You'll see the sinusoidal wave has amplitude modulated, and also its frequency will be modulated. That's not quite so obvious in this picture, but if you look at the frequency of this green wave, you see that it gets larger and smaller again as you move along the x-axis. And this is not a graph of U, the solution of the nonlinear Schrodinger equation, but you can see what U is doing by realizing that U is a complex valued function whose amplitude represents, whose modulus represents the amplitude modulations of the underlying wave, and whose phase represents frequency modulations. So from the modulus and phase of U, you can read off the modulations of this water wave. But again, that's the one-dimensional case. I'm talking a lot about the multi-dimensional case in this talk, where X is an element of d-dimensional space. T is a real variable. So the equation is I times the partial derivative of U with respect to T plus the Laplacian of U in RD plus some nonlinear function of U is equal to 0. And I'm going to specialize right away to this particular nonlinearity, where f of U is a pure power of the modulus of U times U itself, and the power is positive power. P is bigger than 1, so -1 is positive. And this is kind of nonlinearity already is general enough to exhibit all kinds of different behavior. Solutions of this equation exhibit all kinds of different behavior, and just trying to understand the equation with this nonlinearity in RD has occupied a vast amount of the literature over the past 30 years. There's hundreds or maybe thousands of papers about the NLS equation with this nonlinearity. I should mention that sign of the nonlinearity makes a big difference. If I were to put a minus sign in front of this power, I would get what's called the defocusing case. And in that case, the nonlinear Schrodinger equation, the NLS equation, does not have bound states. So I've chosen f of U here to be in the focusing case where bound states aren't possible. And the particular form of this nonlinearity is the way it is because if f of U has this particular form, then it has the symmetries that I've listed on this slide. So symmetries say that if U operate on U by rotating in space, or translating in space and time, or phase shifting U, which means multiplying U by a complex constant of amplitude 1, or dilating U, which I've written down here. You dilate the x variable by a parameter lambda and the t variable by lambda squared, and then multiply U by lambda to the 2 over p minus 1. All these operations on U preserve solutions of nonlinear Schrodinger equation. So if you start with U and convert it to U tilde, you will still have a solution of the nonlinear Schrodinger equation. Galilei and Booth also preserve solutions. So what this is saying is if you're looking at a solution of the equation, but then you change to a moving frame with constant velocity v is a vector, and then multiply by this particular phase function of space and time, then you will still have a solution of the nonlinear Schrodinger equation. So for this nonlinearity, these two functionals are conserved functionals for the equation, meaning that if you have a solution of the equation, then these functionals, the energy, script h, and the mass, are independent of time. And this is called the energy because you can actually write the equation, the nonlinear Schrodinger equation, in Hamiltonian form. You can write it as ut is equal to a skew symmetric operator times the gradient of h. So h is actually the Hamiltonian for this equation and is therefore preserved by the flow of the equation. The mass, it's called the mass, is actually just the square of the L2 norm. It sometimes goes by up as well. So there are two important values of the nonlinearity come up when you're looking at the dynamics of solutions of NLS. They're values P and P. So these are the values of constant P, which appear in the nonlinearity, for which either the mass is invariant under dilations. I mean, these dilations that I wrote on the previous slide. Or, so when P is equal to PM, the mass is invariant under dilations. And when P is equal to PE, energy critical nonlinearity, the energy is invariant under dilations. And PE, there is only a energy critical nonlinearity in the case when D is greater than or equal to 3. When D is equal to 1 or 2, the energy is never invariant under dilations. But I've defined, following convention, I've defined PE to be infinity in that case, because these critical nonlinearities are the boundary between what are usually called subcritical and supercritical nonlinearities. And all subcritical nonlinearities share certain properties, and the properties that you associate with subcritical, sub-energy critical nonlinearities in higher dimensional space are usually valid for all values of P in 1 and 2 dimensional space. So just by convention, we say that in 1 and 2 dimensions, every value of P is energy subcritical. So the critical value is infinity. So here I've summarized a little bit about the well-posedness theory of the NLS in H1. So in the energy subcritical and critical cases, PE, by the way, is bigger than PM. So the mass subcritical cases are a subset of the energy subcritical cases. So in the energy subcritical and critical cases, NLS is locally well-posed in H1. And in that case, so that means solutions of the initial value problem are unique, they exist, and they depend continuously on the initial data. And that's enough to give you, that amount of well-posedness is enough to give you conservation of energy and mass. But if you're in this smaller range of P, the mass subcritical range, then you have not only local well-posedness, but also global well-posedness in H1. And the reason for that is because in the mass subcritical case, which I think I'll mostly just call the subcritical case from now on, when I say subcritical, I mean mass subcritical, then you can bound the H1 norm by a combination of the energy functional and the L2 functional using Galliardo-Nirenberg inequalities. So from the conservation of those functionals, you get an a priori bound on the H1 norm, which allows you to extend the local well-posedness to a global well-posedness. And this is, global well-posedness result is sharp. It's been known since the 1970s from actually a fairly easy proof that Glassy found in the 1970s, that if you get into the mass critical or supercritical cases, then solutions can blow up in H1 in finite time. So you don't have global well-posedness in those cases. In fact, Glassy found that anytime you have initial data with negative energy, then the solution will blow up in finite time. So for this type of nonlinearity, the NLS equation does have standing wave solutions. On the next slide, I'll give an existence result, but they exist for all values of energy supercritical nonlinearities. So they do exist. And what I mean by a bound state solution is a solution of this form. It's a localized solution, which is periodic in time. So it's localized because as a function of x, it's in H1, and it's periodic in time with this particular sinusoidal periodicity. I guess in the physical literature, bound state solutions are any kind of localized solution. They don't necessarily have to be periodic in time, but this is just the way I define bound state solutions for this talk. And it's, if you ask for this kind of a function to be a solution of NLS, that's equivalent to requiring the profile function, phi, the dependence of u on x, to be a solution of this equation. The Laplacian of phi plus the modulus of phi to the pth power is equal to some constant times phi. So this is, it's kind of a nonlinear Schrodinger equation. It's a eigenvalue equation, a nonlinear eigenvalue equation. It's a nonlinear elliptic equation that looks kind of like an eigenvalue equation. This equation is already pretty difficult to solve. It's an open question to characterize what the solutions of this equation look like in d dimensions. But there are special kind of bound state solutions that more is known about. These are ground state solutions. And again, there are several different definitions of ground states. But for this talk, I want to define a ground state to be a bound state solution whose profile phi is a minimizer for this Weinstein functional. So it looks kind of complicated at first, maybe, if you haven't seen it before, but really what it is, it's just the functional that you would try and minimize if you were trying to find the best constant in the Galliard or Nirenberg inequality. I'm talking about the inequality that bounds the LP norm, or the LP plus 1 norm of a function, by some power of the L2 norm of the derivative of u and the L2 norm of u. So if you try and find, so the Galliard or Nirenberg inequality says that this functional is actually bounded below by a positive constant. I believe that's true in the energy subcritical case. And we call a solution a ground state. A bound state solution is called a ground state if the phi actually, the profile function phi actually achieves this best constant in the Galliard or Nirenberg inequality. And this turns out, this definition of ground state, which is kind of elaborate, could be stated much more simply. You could just define a ground state to be a non-negative bound state solution, because that turns out to be equivalent. But that's not obvious at first. In fact, it's a fairly deep result. I've given the more complicated definition at first because it's easier to work with. But you can just think of ground states as being non-negative bound state solutions. So here's a basic classical theorem on the existence and uniqueness of ground state solutions. So I've said underneath the theorem a little bit about its history. So existence of bound states, not necessarily ground states, goes back at least to the work of Strauss and Bernstein-Lyons in the 70s and 80s, but I believe it goes back farther than that, to the 60s at least. And Weinstein was the first to prove existence of ground states. In other words, he proved that there are bound states which actually minimize the Weinstein functional. And this theorem also contains a uniqueness result, which was only proved later by Kwong in '89. And as I mentioned before, it's actually a fairly deep result about ODEs, it turns out. So the theorem says that if you have an energy subcritical nonlinearity, then there will be ground state solutions of the nonlinear Schrodinger equation. They're given by e to the it times q of x. And you can say more about that. You can say that there is a ground state solution which is radially symmetric and which is strictly positive, and its dependence on the radius, on the modulus of x, is that it's strictly decreasing as a function of x. It goes to 0 as x goes to infinity. So one of these exists. There is a radially symmetric non-negative ground state solution. And in fact, every ground state solution is going to be some dilation or translation or phase shift of this non-negative ground state solution. So this is the uniqueness part of the theorem, that there are no other ground states besides the one that you can get from this non-negative ground state solution by symmetry. Just a word about the proof of this. So Weinstein proved the existence of ground state solutions by a concentration compactness argument. He showed that, well, we know that Ju is bounded below. I guess that's obvious because it's a positive functional. So there are going to be sequences in H1 which approach, which are minimizing in the sense that JUN approaches the least possible value. But Weinstein showed that if you have any minimizing sequence, then you can find a subsequence, UNK, which after suitable translations by some sequence XK, will converge strongly in H1. And once you show that, then it's easy to see that the limit has to be a ground state profile for some value of omega, and then you can rescale to get other ground state profiles for other values of omega. So Weinstein did this before proving uniqueness. Uniqueness was proved by Kwong later, and the hard part is on the next slide, but the first steps in the proof of uniqueness would be first to, you can do a little argument to show that every ground state profile is going to be non-negative up to multiplication by some complex number of absolute value 1. That's not so hard. So essentially ground state profiles are negative up to symmetry, non-negative up to symmetry. And then you can use the method of moving planes or the Giedus-Nirenberg theorem to show that, which tells you that if you have a non-negative solution of an elliptic equation like the one that phi satisfies, then it must be radial. So by the method of moving planes, non-negative solutions must be radial, and in fact are decreasing functions of the radius. But the hard part of the proof was, so now it's been reduced to showing that there's a unique non-negative radial solution of this nonlinear elliptic equation in d-dimensional space. Since it's radial, that means what you're actually doing is you're trying to show that the radial Laplacian plus q to the p equals q, that this ODE has a unique non-negative solution. And that's the hard part. That's what Kwong managed to do in '89. He proved that there's only one non-negative solution to this ODE whose derivative at 0 is 0. This comes from assuming that the original solution is radial, and which goes to 0 at infinity. So that establishes the uniqueness part of this theorem. There's a unique non-negative radially symmetric ground state solution of NLS with omega equals 1, and all the other ground state non-negative solutions are dilations of that. So let me finally get to what I mean by non-degeneracy of ground states. So this is something that was proved by Weinstein in '85 for the NLS equation. Except Weinstein didn't quite prove this because his proof relied on the uniqueness of ground states, and that wasn't proved till 4 years later by Kwong. So Weinstein was only able to prove this result for, I think, n equals 1 and n equals 3, because at the time in 1985, those were the only, the d equals 1 and d equals 3, dimensions 1 and 3, because those were the only dimensions in which the uniqueness theorem had been proved up to that point. But once Kwong's result was proved, then Weinstein's argument turned into a complete proof for all dimensions. So what do I mean by non-degeneracy? Well, if you take the equation that ground state solutions satisfy, and then you linearize it about q, so you get this linear operator. Actually, I've multiplied it by -1, so the linear operator is minus the Laplacian of v minus p times q to the p minus 1, the derivative of q to the p times v plus v. Then that linear operator is obviously going to have a kernel, a non-trivial kernel, because if you take the equation that bound states satisfy and differentiate it with respect to any of the variables x1 through xd, then you will see that this linear operator applied to the derivative of q with respect to xi is 0. So these d partial derivatives from x1 to xd all are in the kernel of L. And we define L to be non-degenerate if the kernel of L is spanned by those partial derivatives, if there are no other functions in the kernel of L, if the kernel of L is d-dimensional. So Weinstein stated this fact, and he used it actually to prove stability of ground states. But as I said before, his proof depended on Kwong's uniqueness theorem, which actually hadn't been proved yet. But in 2007, Chang, Gustafsson, Nakanishi, and Tsai wrote a paper in which they pointed out that you can get this non-degeneracy result without having to use Quan's deep uniqueness result, just by a few simple arguments involving Stern-Liouville theory. So this proof that I'm putting up here is actually Weinstein's proof. In most regards, there's just one step where Chang, Gustafsson, Nakanishi, and Tsai realized that you don't have to use, they substituted Weinstein's proof, which used uniqueness, for something else, some simpler argument. So first I wanted to mention that in case d equals 1, there's really nothing to prove if you want to prove non-degeneracy, because remember, we're talking about the solutions of, in the one-dimensional case, this would be the solutions of a second-order ODE, a Sturm-Liouville operator. And the Sturm-Liouville theory says that all the eigenvalues of a second-order differential operator are simple, and since 0 is an eigenvalue, it's simple. That means its kernel is one-dimensional. So that proves the theorem in one dimension. In higher dimensions, Weinstein's idea was first decompose L2 in d-dimensional space, any function in L2 into its spherical harmonic decomposition. So any function v in L2 of Rd can be written, if you'd let r and y be polar coordinates in Rd, r is the radius and y is a x over the modulus of x. Then you can decompose v into spherical harmonics. Ykm is a spherical harmonic of degree k, and there are a certain number of them for each k, indexed by m. And then you multiply ykm of y by a radial function f. And because the L that we're talking about, this linear operator, is invariant under rotations, it follows from some abstract representation theory that it's going to leave the spherical harmonics invariant, which means here that the action of L on V respects the spherical harmonic decomposition. If you take L and apply it to this sum here, the action of L on each of the functions fkm is going to be independent of m and will depend only on k. And the action of L on the radial part of the spherical harmonic of degree k is given by this operator here, which is familiar. This is just what you would get if you tried to write down the Laplacian in polar coordinates in Rd. So it's the Laplacian here in polar coordinates, d squared over dr squared minus the dimension minus 1 over r times ddr, plus this term, which is the angular momentum term, and the Laplacian is applied to spherical harmonics. It's just a constant over r squared minus this potential q of r to the p minus 1 plus 1. So I should have said that what we're looking at here is really a Schrodinger operator in Rd with potential. We're asking about the spectrum of the Schrodinger operator. We're trying to show that 0 is a simple, is a d-dimensional eigenvalue in the spectrum of the Schrodinger operator. So we want to show that the kernel of L is d-dimensional, and what we can do to prove that, or what Weinstein said we can do, is we can look at the kernels of each of these operators L, starting with L0, L1, and then up to infinity, L2, L3, L4. So it turns out that if you just look at the kernel of L1, that already, well, that's a one-dimensional kernel. That's the first observation. So in other words, if you apply L to functions that are spherical harmonics of degree k, then the only way you can get 0 is if the radial part of that is dq dr. And that's obvious. If you look at L1 here, that's obvious from the Perron-Frobenius theorem, because we know that ground states are radially decreasing, so their derivatives are of one sign. dq dr is always negative on 0 to infinity. And we know that dq dr is in the span of L1. The reason for that is because, as I said in the previous slide, del q del xi is in the span of L, and del q del xi is just del q del r times a spherical harmonic of degree 1, namely xi over r. So if you take del q, dq dr and multiply it by xi over r for I equals 1 to d, you'll get all the functions in the kernel of L. So that means that this fact here, that the kernel of L1 is a span of dq/dr, already gives you all of the functions in the kernel of L. And I should have said that the Perron-Frobenius theorem tells you that since this is an eigenfunction for L of one sign, that it has to be simple. So there's only one eigenfunction. The span is, this is a one-dimensional kernel here. So we've already used up all d of the all the dimensions of the kernel of L just in L1. So what we have left to prove is that all the other L's have kernel 0. And that actually follows by very simple arguments. Weinstein already wrote down this argument here. So the fact that the kernel is 0 for all k bigger than 2 follows from this identity, which is obvious if you look at the definition of LK. It just says that LK is a bigger operator than LK minus 1. And so the quadratic of forms associated with LK is bigger than the quadratic of form associated with LK minus 1. And that's just obvious if you look at LK. If you change K, all that happens is this constant term here gets bigger. And it follows from that that the eigenvalues of LK have to be bigger than the eigenvalues of LK minus 1. So this infimum of the spectrum of LK has to be bigger than the infimum of the spectrum of LK minus 1, unless LK has no eigenvalues. But anyway, skipping over, that doesn't matter because in this argument, because the essential spectrum of all these operators is the interval from 1 to infinity. So if there are no eigenvalues, the infimum of the spectrum has to be 1. So in either case, the infimum of the spectrum of LK can't be 0. It has to be bigger than 0. It has to be 1, or it has to be bigger than, if it has an eigenvalue, it has to be bigger than 0. So that means that since 0 is not in the spectrum, then the kernel has to be 0-dimensional. So that was, Weinstein recognized already that that was true. But this part of the proof here is where Weinstein had to use uniqueness, and this is the part of the proof where Chang et al. Realized that you can do a simpler argument. So in this part of the proof, we're trying to show that if you take the operator L0, which is just the radial Laplacian, because k is 0, this term goes away. So you just have the radial Laplacian with potential PQR to the P minus 1. That has a trivial kernel. So this is the step that Weinstein got stuck on. But Chang's argument is the following. We're going to prove that it has a trivial kernel by contradiction. Suppose that you have a non-zero function in the kernel of this radial Laplacian. So V is non-zero, it's a radial function, and L0 of V is equal to 0. Well, then you just observe that these two identities hold, that L of Q is equal to minus P minus 1 Q to the P, and L of this virial kind of function is equal to minus 2Q. Those two identities tell you, it doesn't really matter what these functions are, but they tell you that Q to the P and Q are in the range of L. And since L is self-adjoint on the space of radial functions, that means its kernel must be perpendicular to its range. So anything in the kernel of L has to be perpendicular to both QP and Q. Therefore, it has to be perpendicular. Its L2 inner product with any combination of QP and Q has to be 0. And we're going to get a contradiction from that. And here's where the contradiction comes. You can show, I didn't mention it, but you can show that since we're talking about a ground space here, the operator L has to have Morse index 1. In other words, it can only have one negative eigenvalue, and the eigenvalue has to be simple. That's just a general, fairly straightforward fact. So that means 0 for this operator, L naught has to be the second eigenvalue. And Sturm-Liouville theory tells you that for the second eigenvalue of a Sturm-Liouville operator, it has to have exactly 1 0 on the interval 0 to infinity. So, but on the other hand, since Q of R is decreasing, it's easy to see that you can find some combination of Q and its power Q to the P, which makes this combination have a 0 at exactly the same spot that V did. So now we have a contradiction because we have two functions, V and Q to the P minus mu times Q. they both have exactly 1 0 at exactly the same spot. So when you multiply them together, you're going to get a product which has the same sign everywhere, and so therefore cannot integrate to 0. So it's a simple argument just based on Sturm-Liouville theory that doesn't end around this difficult problem of proving that the radial Laplacian has 0 kernel in this case. So now what I'd like to talk about is, so that was a lot of work. Remember what we just proved, or was to prove that L is non-degenerate. And I would like to show this beautiful result of Frank and Lenzman about how you can use non-degeneracy to prove uniqueness. So you will see a lot in the literature that non-degeneracy of bound states is closely related to uniqueness of bound states, but the connection is a little bit tricky. Weinstein already mentioned that. And in fact, he couldn't prove uniqueness of bound states. He could prove non-degeneracy, but he couldn't prove uniqueness. That was only done later by Kwong. So what we're going to do next is prove uniqueness of ground states following an argument of Frank and Lenzman for the fractional nonlinear Schrodinger equation using non-degeneracy. So Frank and Lenzman's proof of uniqueness of ground states is going to first show that you have non-degeneracy of ground states following an argument like the one we just gave, and then use that to prove uniqueness of ground states, which I think is an amazing result. So let me just briefly talk about the fractional nonlinear Schrodinger equation. It looks just like the nonlinear Schrodinger equation, but it has a fractional Laplacian here, which means, and the fractional Laplacian is defined as a Fourier multiplier operator. You take the Fourier transform of u, multiply by xi to the 2s instead of just xi squared, which would give you the ordinary Laplacian, and then take the inverse Fourier transform. So you can think of this as being a model equation for more general types of dispersion than the NLS equation. The energy functional looks very similar for the fractional nonlinear Schrodinger equation. You just replace Laplacian by the fractional Laplacian. And the energy subcritical case is given by this formula here. And you can show that, so that's the energy subcritical case in dimensions. Let's see, I guess it depends on whether S is less than D over 2 or bigger than or equal to D over 2. But if D is equal to 2 or greater, then you're only going to be, we're only considering the case when S is less than D over 2, because S is between 0 and 1. But if you're talking about D equals 1, then for S bigger than a half, all values of P are energy subcritical. And the analog of the existence theorem for ground states for the fractional nonlinear Schrodinger equation, the same methods used to prove existence for the NLS work for the fractional NLS. You can prove existence of ground states by minimizing this version of the Weinstein functional. That again is a concentration compactness argument. And that will be true, minimizer will exist for all subcritical, energy critical nonlinearities. And again, we're going to say that the ground state is non-degenerate if this linearized operator associated with it has kernel equal to the span of the partial derivatives with respect to xi. Okay, so I said that Frank and Lenzman proved uniqueness for ground states. Actually, uniqueness, I have to be careful, uniqueness for non-negative ground states. I don't think it's known that, I don't think there is a uniqueness result for general ground states, just for non-negative ground states. But it's an amazing result, because if you look at what was known before they proved their result about this kind of question, it was almost nothing. So uniqueness problems for nonlinear elliptic equations are notoriously difficult. People would like to have them, but they have trouble proving them. And here I've listed all the non-perturbative uniqueness results that were known before Frank and Lenzman about solutions of this equation. By non-perturbative, I mean not one that you get just by perturbing a uniqueness result for a specific value of S. So it was known, Kwong had proved uniqueness for the regular nonlinear Schrodinger equation, which was S equal 1 for all subcritical nonlinearities. But he had to use ODE techniques to do this, which would not work for the fractional nonlinear Schrodinger equation. Amick and Toland proved uniqueness in the one-dimensional case, but only for the specific nonlinearity p equals 2 and the specific fractional derivative minus Laplacian to the 1/2, which is the Hilbert transform, or the derivative of the Hilbert transform. And the reason they had to restrict to those specific values is because they use heavily the fact that in that case, you have integrability. Actually, this equation comes up as the equation for solitary wave solutions of the Benjamin-Ono equation, which is a completely integrable equation. And they used a lot of special properties of the equation in that case. And these two results are it. There was nothing else that had been proved yet, non-perturbative, about uniqueness results. So here's Frank and Lesman's uniqueness result. It appeared in two papers. First, they proved it in 2013 for the one-dimensional case. And that almost constituted a proof for the higher dimensional case, but they were not able to quite do that in 2013. But then in a paper with Silvestri in 2015, they filled in the missing piece and got the general higher dimensional case for non-negative solutions. So their theorem is that for all values of S between 0 and 1 and all energy subcritical nonlinearities in all dimensions, that, skipping to the second part, that non-negative ground state solutions of this equation are unique up to translation. And the way they proved that is they first showed that this linear operator is non-degenerate. So how does that work? So how do you get from nondegeneracy, which is a statement about the linearized operator associated with Q, a local statement in some sense, how do you get from that to a full nonlinear proof about uniqueness? So their idea was you're going to use the nondegeneracy to set up a continuation argument from S equal 1. So we know that uniqueness is true in all cases for S equal 1, and we want to continue the uniqueness all the way down to S equals 0 using nondegeneracy. That's going to be the condition that you need to apply implicit function theorem to set up branches of solutions. So first, how did they prove nondegeneracy? Well, this turned out, we can explain pretty simply how they did this, because it turned out that the same proof for fractional NLS will work for NLS once you realize that you can use the result of Chang et al. To prove nondegeneracy. So remember, the first nondegeneracy proof of Weinstein needed uniqueness. We can't use that here because we're trying to use nondegeneracy to prove uniqueness. But Chang et al. Realized that you don't need uniqueness to prove nondegeneracy. So Frank and Lensman's idea was, okay, we can prove nondegeneracy first without uniqueness, and then use that to prove uniqueness. They could only do that in one dimension, as I said at first, but then they realized how to do it later in D dimensions. So in order to do it, what you need to do is somehow come up with some substitute for Sturm-Liouville theory for this non-local equation. Because remember, in Chang's proof, there was one point where we needed to use Sturm-Liouville, one crucial point where we needed to use Sturm-Liouville theory. It was when this function v that we talked about had only one 0. Well, it turns out the same thing is true for this non-local equation, that if, so this lemma says that that's the case. If you have an eigenfunction for any fractional Schrodinger operator with any radial decreasing potential corresponding to the second smallest eigenvalue, then V will change sign exactly once on 0 infinity, kind of like what you would expect in the local case, in the Sturm-Liouville case. And another point where the analysis differs from the local case is this first statement here, which is totally obvious when you're talking about S equals 1. It just says if you have a solution of this linear equation with 0 initial data, which is radial, remember radial means that the derivative at 0 is equal to 0, then the solution must be 0. So in the local case, this just follows immediately, because if you have a solution of a second order equation and we're talking about an ODE here because we're talking about radial functions. A second order ODE with zero initial data and zero derivative, then it has to be zero by the uniqueness theorem for second order ODEs. But in the non-local case, that's not obvious at all. And let me just skip over this part briefly. The basic idea that they used is to analyze this non-local problem by doing a Caffarelli-Silvestri extension. Caffarelli-Silvestri, I don't think they were the first people to do it, but they were the first people to make heavy use of it. Figured out that you could analyze this fractional Laplacian by viewing it as the Dirichlet-Neumann map for this nonlinear equation in one higher dimensional space. By that I mean that if you have a function f on Rd, you can get its fractional derivative minus Laplacian to the s of f by using f as the Dirichlet data for this elliptic equation, solving this elliptic equation in one higher dimensional space with f as boundary data, then taking the normal derivative of w and restricting again to the boundary, and that will give you a constant times the minus Laplacian to the s of f. So it's a Dirichlet. So this operator is the Dirichlet-Neumann map for this local. The point is that this is a local equation in d+1 dimensional space. And for a local equation, you can analyze the nodal domains using Courant's argument. There's the Courant nodal domain theorem, for example, which gives you estimates on the number of nodal domains a given eigenfunction can have. And that's what enables you to prove this lemma. I think I'll skip over the details of that, saying any more about the details, except to say that this first part here, this was the part that Frank and Lensman were not able to prove in their 2013 paper. This was the only part in their 2013 paper that they were not able to do in higher dimensions. But then in their 2015 paper, they realized that they could use this kind of remarkable monotonicity result of Cabret and Cyr to prove this first part of this lemma. So, okay, so skipping to the end of that, we have this lemma, and then once you prove the lemma, then the same argument that I gave before for NLS will prove nondegeneracy for fractional NLS. So at this point, we've proved the nondegeneracy statement of this theorem, that if you have a non-negative ground state solution, then L is nondegenerate. And now it turns out that once you have nondegeneracy, you have this very nice, attractive, simple argument for, let's see, for proving uniqueness for ground states. But I have to state this lemma first before giving the nice simple argument. So the lemma is, so we're going to do a continuation argument. And the lemma tells you that you can do that if you start with a non-negative ground state solution of this equation at a specific value of s, then you can continue it to a curve of solutions of this equation that goes all the way to s equals 1. So you can start at s and extend to a larger interval of s, but you don't stop until you get to s equals 1. And this is, of course, the crucial ingredient in the idea of Frank and Lensman's argument. You want to continue your solutions all the way to s equals 1 where you have uniqueness. Now, when you do this, when you do this, you use nondegeneracy, because nondegeneracy turns out to be exactly the condition that you need to apply the implicit function theorem to find solutions of this equation. If you take this equation 3 and take its derivative with respect to q, that gives you the operator L, and saying that the L is has non-zero kernel is exactly saying that you have nondegeneracy. So let me see, in the interest of time, let me just, I did want to say that when you continue this, when you do this continuation argument, you don't necessarily get ground states. They aren't able to show that, but you do get a branch of solutions with Morse index 1, and that's all you need in order to prove the nondegeneracy argument that I had on the previous slide. So this argument here only required, the nondegeneracy part of this theorem only requires Q to have Morse index 1. So using the implicit function theorem and the non-degeneracy, you can continue your ground state solution to a branch of solutions, which aren't necessarily ground states, but they are solutions, all the way to s equals 1. And the hard part of this proof here is in this box, which I'm skipping over. I'm gliding over the hard part. You have to get estimates on QS that allow you to pass to the limit as you approach the maximal value of S. And that's what you use to show that S, the maximal value, cannot be less than 1. It has to equal 1. Because if you can pass to the limit, then you get a ground state at S, and then you can continue further, violating maximality. So this part in the box was the real hard part that Frank and Lesman had to do, the part that required the most intuition and the most computations. But now that you've got that out of the way, now that you've got this lemma proved, then the proof of uniqueness is very simple and conceptual. You just argue by contradiction. So you want to prove you have uniqueness of ground states. So you assume that you don't. You assume that you have two distinct solutions, Q and Q tilde, for a specific value of S. And you continue both of them to S equals 1, which we've just seen that you can do. And you do this with local uniqueness. Local uniqueness comes from the implicit function theorem. So in any neighborhood of any of these solutions, there's only going to be one solution. Now, since you can continue both of these solutions to S equals 1, we know that the solution for S equals 1 is unique. So both of these branches of solutions have to be heading towards the same unique ground state solution, which exists for S equals 1. So at some point, they have to get it within some small neighborhood of this solution where local uniqueness holds. So that means at some point, these two branches have to coincide. They can't go all the way to S equals 1 without coinciding at some point. But then that would violate local uniqueness, whether it happens in this small neighborhood or whether it happens earlier. If the two branches coincide, that's a violation of the local uniqueness that you get from the implicit function theorem. So it's impossible to have two separate branches converging to the same point at Q equals 1, and that ends the proof. So I'm short on time here. What I just showed was that you can use non-degeneracy, the linear property, to prove a nonlinear uniqueness result. And I'm not going to have time to talk about this. This is a much more classical result of Weinstein, which is about stability of the ground state. So Weinstein proved nonlinear stability of ground state solutions of NLS in any dimension. And what he actually proved was orbital stability, which says that if you start with if you start with a solution whose initial data is near any bound state profile, then you will stay near the set of phase shifts and translations of a bound state. So it says that the orbit of the bound state solution is stable in H1 for the initial value problem. And Weinstein proved that this was true for all mass subcritical nonlinearities. I'll skip over this. This was first proved by Cazenave and Lyons. But the point I wanted to make is that Cazenave and Lyons' proof required Kwong's uniqueness theorem. If you don't have Kwong's uniqueness theorem, which is again a very deep theorem about ODEs, then Cazenave and Lyons' proof only gave a weaker notion of stability. It doesn't give orbital stability. In order to get the strengthened notion of stability, orbital stability, you need Kwong's uniqueness theorem. What Weinstein did is he obtained the strength and stability without the uniqueness theorem. Well, actually did kind of need the uniqueness theorem because he used the non-degeneracy of L to prove uniqueness. But as we've just seen, as Chang showed, you don't need Kwong's uniqueness theorem to prove non-degeneracy. So Weinstein's proof with that observation gives you a way of proving uniqueness, proving stability of ground states without having to prove uniqueness of ground states, only needing the non-degeneracy of ground states. This is a classic argument, but I think I'm running out of time rapidly, so I'll skip over this and just leave it as a slide up here. So I wanted to finish by saying a few more things about how non-degeneracy comes up. So non-degeneracy of L does come up if you're trying to prove instability of ground state solutions in the supercritical case. Well, you don't need it to prove instability. That's done by a simple argument that's due to date back to Weinstein. And a more complicated argument, Weinstein did the critical case, Berestecki and Kavanaugh did the supercritical case, but they didn't need to use non-degeneracy necessarily. But if you want to get more detailed information than they had about the blow up, so it turns out that ground state solutions are strongly unstable. You can approximate a ground state solution very closely by initial data, which blows up in finite time. And if you want to understand this blow up better, you need to know the non-degeneracy of L. I've also got a slide here about higher bound states. I think I will just skip over most of this slide completely. There are some results, but I do want to say a couple of things quickly. There is an open problem hidden in this slide somewhere, which is that if you have a mass subcritical nonlinearity, then it's an open question of whether there are bound states which are radial, but they're not non-negative. They have arbitrary number of zeros, sign changes, and it's unknown whether these radial higher states, non-ground states, are stable. So that's still an open question. But for supercritical nonlinearities, they have been proved to be orbitally unstable. And there's a variety of results on other higher states, but none of them have. Okay, the field is still kind of wide open. We don't really know much about higher bound states or their stability in general. At the end, I mentioned that there's a recent result, a non-degeneracy result for these higher bound states, and I think this is about one of the only non-degeneracy results known to date for these higher bound states. So let me just finish with a quick description of the soliton resolution conjecture. This is some kind of ill-defined conjecture which says that if you're trying to solve an NLS equation with general initial data in H1, then at large times, what you will see is a finite collection of bound state traveling wave solutions. So these are the bound states that we've been talking about, except boosted by a Galilean boost, and other traveling wave bound states with different frequencies and velocities. But this hasn't been formulated precisely because we don't know exactly what bound states look like in higher dimensions. We know, well, all we know so far is that radial ground states are unique, that non-negative ground states are unique, but we don't know anything about what general bound state solutions look like. So what people have been trying to do towards this conjecture is try and prove the asymptotic stability of stable ground states and try and prove the instability of higher bound states. But both these questions remain largely open, except in the integrable case, the one-dimensional case when p is equal to 3. So this is the integrable nonlinear one-dimensional Schrodinger equation, cubic nonlinearity. And in that case, recently, a version of the soliton resolution conjecture has been proved by Borghese, Jenkins, and McLaughlin. They used the integrability, of course, very heavily. They did it for generic initial data, not for all initial data. And there are initial data which don't satisfy their conditions. And in a weighted subleft space, so not exactly H1, but at least in H11. I think this condition here rules out breather solutions. So their result doesn't include breather solutions. Asymptotic stability of ground states had been proved earlier by Kukhania and Polinovsky in 14 or some version. But again, the field is wide open. I'll end with this quote from this review article of Martel, Kowalczyk, and Munoz. They say that to the author's knowledge, no result of asymptotic stability, so let alone the soliton resolution conjecture, just asymptotic stability for ground states, no result has been fully proved for any pure power nonlinear Schrodinger equation with stable solitons, except in the integrable cubic 1D NLS case. And one of the places where the existing results fail to be complete results is that they often make assumptions about the spectrum of the linearized operator. This L is the same operator we've been talking about previously. This L tilde is a related operator. This script L, the spectrum of this operator is much harder to understand than the spectrum of L and L tilde. Bernard would be an expert on this because he looks at these kind of linearized operators in the periodic case. Anyway, it's very difficult to get results about the spectrum of this operator, and so that's why many of these questions, that's why asymptotic stability remains open in most cases. So sorry I went a bit over, but that's the end of my talk. And thank you for sitting through.
Any questions? No? Okay, if there's no last questions, let's give the speaker a round of applause. Thank you.
Thank you.
Thank you, John.